Right. So, let's start with trying to put all these singular integrals to work over here. So, we have seen that when we have integral of the form 1 by x dx, I have to do the integration a little bit carefully. So, one is the principal value part and the second is the residue part, right. So, these are our two equations over here, and because of this grad g dot n hat, there is going to be a problem, right, because in this contour integral of mine, let us say r prime is fixed over here and r is running over the entire contour. So, there will be some one point at which r hits this r prime, and that is the issue that we have to care about, right. So, for each of these integrals, I have to modify the contour in the correct way. Okay. So, let us look at equation 1. Okay. So, this is equation 1, this is my okay, and my point here r prime I have put over here. Okay. So, equation 1 is that r prime belongs to V2. Okay. So, I am coming along from here and I want to make sure that r prime belongs to V2, right. So, if I just write down what is V1 and V2 over here, this is V1 and V2. So, which way should the contour bend? It should bend in such a way that r prime still belongs to V2. So, the way to make this small bend is now the point r prime is inside V2, because I have changed the surface just a little bit, right. And this I will zoom in and show you. What I am doing is something like this. It is a very small circle, the radius of which is epsilon, and epsilon is tending to 0. So, I have in the limit I have not really changed the surface. I am going to take the limit epsilon tending to 0. So, r prime, which is this point over here, stays in V2. No, r prime is remaining at that point. I am changing the boundary around it. The boundary is the boundary between V1 and V2, and I have pushed the boundary little bit this way, but r prime is still there. R prime is not moving, I am moving the boundary a little bit. So, I had started by saying I am putting r prime on the boundary, okay, and boundary was okay because boundary is both in V1 and V2. Then we said that 1 by x dx has a problem. So, I have to move the boundary a little bit. If I move the boundary the other way, then r prime will fall into V1. Now, it is staying in V2, right. So, that is the small boundary modification for equation 1. For equation 2, the same logic will give me a different contour, right. So, this is again V1 and V2. So, this is my point over here, that is r prime. So, I must modify this in this way. I am exaggerating it to show you very clearly which way I am bending the boundary, but obviously that is a circle of radius epsilon which will go to 0. So, in this equation now r prime, which is this guy, continues to stay in V1. Okay. So, that is how we will modify these boundaries. Okay. Now, you might wonder, I am going to take the limit epsilon tends to 0. So, does it really matter how I bend it? Finally, I am going to take epsilon tending to 0. Whether the boundary bends downwards or upwards, will you get different answers, right. So, it depends on the integrand. We will see whether it depends. We will see whether the integral matters one way or the other. Alright. So, is this part is clear? So, this is a very important part. I have sort of given the answer away already. It matters which way you bend the contour. You get different answers in both cases. Okay. So, let's see how to do this correctly. Okay. All right. So, now let's evaluate these integrals. Okay. So, before I show you the exact calculation, there is some very basic mistakes that can happen in integration. So, to avoid those, I am going to show you some very simple integration. Okay. So, case 1 is this. I am integrating from here to here, okay, and let us say my differential element is dl over here, okay, and I am going from 0 to L. Okay. So, what is the physical interpretation of this? If I just have integral 0 to L dl, what is the physical interpretation? What is the answer first of all? L, right. What am I doing? I have measured, so to speak, the length of the string between 0 and L, right. Even a class 11 student will say answer is 0 to L, right. Now, let us do the same calculation in a slightly different way. So, supposing I have okay. So, I am going from here to here, from this point over here to this point over here, and I want to evaluate let us call this point A and let us call this B. Okay. So, I am going from the point A to B along the contour, and I want to find out integral dl. Okay. I am staying and the integral is along this contour, right. So, if this is a semicircle of radius epsilon, coming from case 1 over here, what will you say this answer is? Length of the string, which is pi epsilon. That is correct. Okay. Now, on the other hand, if you decided to do this integral using, let us say, polar coordinates, right. So, supposing you wrote this like this, that this is your theta and you are integrating like this. So, what are the limits of integration? From where to where? No, where am I starting from? What is the original starting point? Minus pi or pi? Why minus pi? I could write pi also, and final integration point is 0, and what is the differential element? dl r d theta, which is epsilon d theta. What do you get? You get minus pi epsilon. So, what is the catch in this? I should have got pi epsilon because I am measuring the length of this string. Right. So, d theta is pointing in the plus d theta is in which direction? It is in the clockwise direction over here, right, anti-clockwise direction, right, but dl is in the clockwise direction, right. So, dl is actually minus d theta, minus epsilon d theta. So, that is one mistake that you could do if you did not do this integral carefully. Okay. So, in fact, so this is wrong. What we should be doing is, let us say, pi to 0 epsilon minus d theta, and then I get the correct answer, pi epsilon. Okay. So, these are some of the things that you have to be careful about when we evaluate this integral. Okay. So, all right, now that we have the simple case out of the way, let's look at our the integral that we have. So, what is our integral? So, I have in one case, so we look back over here, one case it is going up and the other case is going down, right. So, let us take the up case first. So, that is case A. So, that is right. Right. What is our integrand over here? So, let us call this S plus. Okay, so, it is on the positive side. So, it is integral over S plus and grad g r r prime dot n hat dl. That is the term that we are trying to calculate. Which way is n hat? Which way is n hat? Upwards or downwards? Look back here. Which way was n hat over here? This was n hat, and in this also this was n hat. So, n hat continues to be, so for example, n hat is here like this, and over from here it is radially outwards, fine. Now, what is grad g dot n hat? So, grad g is we had written it as minus j k by 4 h 1 2 k rho r prime. Is that correct, or am I off by a minus sign? Well, we can just check back. We had derived grad g previously. Grad g, see, okay, grad g is a plus j k by 4 h 1 2, right? So, let us use the correct expression over here. So, there is no minus sign over here. Fine. Now, what was r over here? This was the unit vector for r minus r prime, right? That was my okay. So, now let us look at this integral over here, which n hat is in. So, this is my, this point over here, this is my r prime, and let us say this is my point r. So, r minus r hat, which way is it pointing? I mean, so r minus r hat is my radially outward vector, and along this circle S plus, which way is n hat? Same direction, right. So, over here n hat is equal to r hat, r minus r prime, because r is here, r minus r prime is always going to be like this. R prime is fixed to be the center of this semicircle. That is the point that is fixed, the testing point. R is the variable of integration. I am going from here over this circle and like this, correct. So, what I am evaluating is only the residue part, not the principal value. The principal value ends over here and starts over here, right. So, this is the only the S plus integral is what I am calculating. So, n hat is equal to r hat, right. So, when I evaluate sort of put everything inside over here, this the direction of grad g and n hat, what should I get? Direction of grad g is r hat, normal is also r hat, I get a 1, right. So, I can write all the constants out, j k by 4 integral. Now, what should I write? What can I will write the limits of integration as pi to 0, as we did in the simple example, pi to 0, and what is so h 1 2 k rho, and what else? Epsilon minus epsilon d theta, then I will get the correct interpretation. For example, if I put h 1 instead of h 1 2, I write 1, I should get the length of this string, which I will get if I follow this recipe. Okay. Now, now is where I use the approximation for h 1 2, because I am going to take the limit epsilon tending to 0. So, I should use that approximation, right. So, that approximation which we have seen before, that is the part that we are going to use. Okay. Okay. So, we are going to, when we take the limit epsilon tends to 0, okay. So, in this case over here, what is, let us just actually write it all out. So, it is minus j k epsilon by 4 integral pi to 0, okay. And so, I will just substitute. So, I will have k epsilon by 2 plus j by pi 2 by k epsilon d theta. Is that correct? I have just substituted everything that I know. And I know that finally I am going to take the limit, let us call this I 1. So, I 1, I am going to take the limit epsilon tending to 0. So, without evaluating this integral completely, what can you say about the real part in the limit? I will get epsilon squared and the length of the circle, right. So, semicircle. So, that is going to go to 0. The term that is left is what is the term that is left? only the second term, right? So, I am going to get minus j k epsilon by 4 into j 2 by pi k 1 by epsilon. Okay. Into minus pi. Right. That's the only thing that is left. So, what has happened to the epsilons? Epsilons have gone away. 1 k has also gone. Right. There is a minus j into j, that is plus 1, and left with a minus 1. So, the answer is 1 by 2 or minus 1 by 2? Minus 1 by 2, right? The minus goes away and j into j is minus 1. I get a minus half. Yeah, fairly clear. Now, let us come to the other case. The other case is case B, where I have a very similar but a oppositely deformed contour. This is how it is. This is my point r prime. This is my point r. Which way is n hat? Same as before. Yeah, it has to be outwards. So, on this contour, this is my n hat, right? Which way is my this vector r? Upwards or downwards? Downwards, right? Because it is r minus r hat, r minus r prime rather. So, this is my r hat. Okay. So, in this integral now I2, I can write as s minus grad g r prime dot n hat dl. Okay. What happens? So, I will write j k by 4. Okay. Now, I will use the same limits pi to 0 because I should get the length. Whether I go upwards or downwards, I should get the length of the string. Okay. So, let us not complicate that, let us just keep it as pi to 0. Okay. And h12 k rho now is the term which I have to be careful of, r hat dot n hat, which is going to give me now a minus sign, right. So, there is a minus 1 and I have a minus epsilon d theta, right. That is all, yeah, that is what I have left. So, it is identical to the term above except for one extra minus sign, right. So, what should I get? Plus 1 by 2, right. So, it did matter how I did the integration. In one case I get a minus half, in the other case I get a plus half. So, it is suggesting that grad g has a discontinuity across the surface, right. If I approach from bottom or if I approach from top, there is a difference over here. Okay. So, when we look back at all the terms that we had in the integration, right, this was the only problematic term. When I looked at the term involving integral of g1, even if there was a singularity, it was the integral of log x that turned out to be finite. So, there was no problem. This was the only problematic term, and this is how you sort of do it carefully. And this is a characteristic feature of all surface formulations where there is a point at which there is a singularity, and in the case of 2D you had g and grad g was not integrable. Also in the case of 3D you will have g and grad g will not be integrable. So, you have to deform the surface correspondingly. But in 3D it will not be a line that you are deforming, it is a surface that you are putting a hemispherical bowl around. So, that integration becomes a little bit more challenging. Okay. But the idea is the same, there is going to be a discontinuity of 1 on both sides of the thing. Okay. So, that brings us to an end of the part of surface integral equations. Okay. So, before we go any further, is this part clear how we evaluated grad g dot n hat or any other questions on it?